Okay, so as I hinted in the previous lecture, I'm going to do today something different than a regular lecture about solid state physics, and I'm going to talk about a couple of characters that we met in the previous lecture, meaning Einstein and Leonard, and their connection to the Nazi Party's stand on physics. Now, this could seem very strange. Why should a political party have a stand on a scientific issue? And in this case, it was a very strong stand that caused all kinds of actions during a decade and a half of the Nazi power in Germany. And, well, one can always argue that in things that are directly connected to political issues like law or social sciences and things like that, parties can have a standing regarding all kinds of issues because it has a direct effect on what is happening, first of all. Second of all, these are not exact sciences. You could always argue and put in your own point of view into them, and at least partially the results that you get regarding the scientific answer have a non-objective component in them. But come on, physics. You'll vote in the parliament to cancel gravitation. Well, you can do it, but it won't help you much. Though, interestingly, in a place that we associate with a very democratic society, the US, the legislature in Indiana was about to vote about the value of pi. So strange things happen. A very interesting story, and anyone who's interested in it could Google value of pi Indiana legislator and read an interesting story from 1890. But how come in something that is exact science, politics plays such an important role? Well, we can say, well, we have seen also other examples with catastrophic results. Russia during the time that it was Soviet Union, some biologist by the name of Lashenko had an idea that he can improve crops by a certain method. Completely bogus, doesn't work, but Stalin loved the idea and promoted it. And this Lashenko also had other ideas like genetics is a scam, there's no such thing as genetics. And millions of, if not 10 of millions people, mainly in Ukraine at the 1930s, starved to death because they tried to implement these methods to improve food production. So we see that even things that should be clear-cut and things that can be proved scientifically, objectively, still political parties can take a stand. But back to Nazi Germany and how did they come to have a stand about problems in physics? Okay, so like a lot of things in physics in the 20th century, the story starts with Einstein. And I don't know how many of you know about Einstein's early life, but I guess that the myth that Einstein was a bad student somehow diffused. Is it? At least a few people here heard this claim. So the truth is Einstein wasn't a bad student. In mathematics, physics, and things like that, he was a straight A student. In other things, also quite good. Einstein, nevertheless, couldn't stomach the German educational system. At the time, we are talking about the time when Germany was still an empire under the rule of the Kaiser, emperor in English. As many other aspects of German society, it was very militarized, very ordered, very hierarchical, and that kind of educational system Einstein couldn't stand. He just rebelled against it. Einstein's father and I think also his uncle were actually industrialists working on electrification, electric networks and things like that. That was the 1880s and the 1890s, a time that most cities in Europe had started to build their electrical infrastructure. We are nowadays so used that there is such an infrastructure that we don't even understand how much work was put into building this infrastructure. They worked in Munich, in the southern part of Germany, Bavaria to be exact, and their business didn't go well. And they moved to Italy, to Milan, and there they had more success. But as any good parent, and especially as any good German parent, when they moved to Italy, Einstein was there around 14 or 15 years old, and they told him, look, we want you to finish your matriculation, your graduation from high school in Germany, because Germany is a good educational system, Italy is Italians. And you'll stay here and we'll move to Italy, you'll stay here and finish high school. After a few months he just left, didn't finish high school there, and went to Italy, and then they more or less, like any good parent, looked on him and said, excuse me, you won't finish high school? And he said, well, I promise you I'll finish high school by myself. He went to Switzerland and had some problems actually to finish high school because they required there, as a state that had not only bilingual, trilingual states. Switzerland speaks German, French and Italian, depending on what area. They required you that if you're doing the matriculation in German, you have to also take French, and Einstein apparently wasn't very good in languages, and the first time he took French he failed and had to wait a year in order to finish high school there, and then went to Switzerland and finished his undergraduate work. All of you know the stories that he couldn't find work, went to the patent office, worked there as a clerk, and within 1 year revolutionized physics by a set of 4 papers in different subjects. Most well known is basically the special relativity, but also on the photoelectric effect, introducing photons, and in basically the first proof that material is composed of molecules by osmosis and diffusion, Brownian motion. So a very productive year in the patent office. Anyway, Einstein not only left Germany, but he was so crossed with the German systems that he renounced his German citizenship. Said, I want to become a Swiss citizen. I don't want to have anything to do with Germany. Life goes on. He gets his first appointment as a professor in the university. And then there is a series of... he moves from university to university every year or two for two good reasons. One, to get a higher salary. He already had a family, young children, and needed more money. And the second is that, like a lot of people in academia, he didn't like to teach. And each point he was lured to by getting a promise that he'll have a lighter course schedule. So he moved here and there. He was also in Prague, in Bern, Zurich, and I'm perhaps missing a place or two. And then in 1912 came the invitation for him to come to Berlin, the capital of Germany and the main scientific city in Germany, to come and be a professor in the Prussian Academy of Science. Very prestigious, good salary, and also a promise of no teaching at all. Okay, so on one hand, his feelings toward Germany is clear, but on the other hand, good conditions. So he took it, he went to Berlin. Not a very good time, because 1914, World War I starts. And World War I, Germany, Austro-Hungary, Turkey against more or less the rest of the world. Then, something that we're familiar even from what happens here, professors in the university are sucked into politics. Why? The Germans, when they invade Belgium, burn the library of the University of Louvain by mistake or by intention, depends on what side you stand. It was a very famous library, and all over Europe knew about the manuscripts and important books that were there, and it created an outrage mainly in the West, and people came out with this statement that Germans are destroying civilization, just destroying culture, burning up universities, how terrible. And Germans actually, which always thought of themselves as the most cultured and scientifically advanced nation in Europe, felt very bad about it, and they came with a petition that they signed almost all the leading professors in Germany, stating that the world doesn't understand. German war is for culture and advancement of science, and all the others are standing in the way, and all civilized nations should support the Germany in their aims. Okay, so as I said, almost all German professors signed this letter, except for 4 people, one of them Einstein, which came with another petition that said that all civilized nations should stop war and find another way to set their differences in peaceful ways. Okay, the war finished, Germany lost, and it's, well, nowadays it's 100 years since then, it's hard to grasp what a revolution it was in Germany, because Germany went from being a very ordered society ruled by an emperor to a democracy. Not exactly that they chose democracy. Democracy was imposed on them from outside, and as we know from recent experience, imposing democracy from outside not always works very well. Look what happened to Iraq. It was more or less a state of anarchy in Germany, infighting, gangs of discharged soldiers against the militias of communists and against militias of right-wing people all over the place. Heisenberg, let's say, tells us as a teenager he was given a gun and sent to protect his home from the communists in Minsk. So it's a state of extreme agitation, extreme chaos. At this time, a government nevertheless is set in Germany, and this government, unfortunately from the historical point of view, has a huge representation of Jews in it, because traditionally the more liberal democracy-leaning faction had a large percentage of Jews, and Einstein, naturally, according to his convictions, was more close to this government. Now, Einstein was at this point in a very, very special position from the point of view of public relations. What happened in 1919?
The Fourth War?
The solar eclipse that proved the general relativity?
Suddenly there is a measurement that shows that Einstein's theory was correct, and he becomes the leading intellectual, the leading scientist in the world. And he comes from this disgraced nation, Germany. Nobody looks on the fine print the fact that he renounced his German citizenship a decade and a half. For he's a German scientist, and he's the most famous scientist in the world. And at the same time, there was an interesting situation where, as a response perhaps to this petition of the German professors 3-4 years before that, as a response to the war, German scientists were banned from any international gatherings, and weren't invited not to conferences, not to publish in external journals. More or less an academic boycott on Germany. Academic boycott, yes, but Einstein, that was known as someone who opposed the German policy, and was known as someone that thought different than the rest of Germany, and was this renowned scientist, was invited, and the government tried to use him also to improve its relation with other governments, because you have someone that's famous and can speak for you, why not use him? On the other hand, he became identified with the current government, with the democratic forces, with left-leaning politics. All these things were personified by Einstein. Okay, 1920, 21, 22. There's a start of a counter-reaction of nationalistic right-wing politics in Germany. If you know your history, 1922 is the first point where Hitler comes on the stage with the beer putsch in Munich. Nazis weren't the prominent force then, but definitely one of many groups that were going around and basically coming with the statement, "Let's make Germany great again." And here you stand at a position where you have someone very prominent that is identified with the current government that you can't stand. And how do you attack him? How you discredit him? Well, the answer that they came up with basically convince everyone that he is just an impostor. The reason that he gets all this fame around in the world, general relativity, special relativity, all the things that people were aware of and thought as a great achievement, you say it's not correct. It's just rubbish. Okay. Well, a few guys drinking in a beer garden, no one will listen to these guys because what do they know about physics? But unfortunately, at the same time, two German Nobel laureates, Leonard is one of them, and Stark. Did you heard about Stark because he appears in quantum mechanics and the Stark effect, the spectrum of an atom in a strong electric field. So two prominent physicists come and say, well, Einstein is wrong. We are leading physicists, we have Nobel Prizes, no one can argue that we don't understand about what we are talking. Einstein is wrong. Now these two gentlemen not only came with these statements, also joined the Nazi Party early on in 1923, 24, from the first people that joined in, and set out not only to discredit Einstein, but to put their ideas under a wider intellectual standing. And they came out with this theory that basically physics went wrong in the beginning of the 20th century. What does it mean physics went wrong in the beginning of 20th century? Physics went wrong in the same way that literature, painting, all other intellectual endeavors went wrong in that time. All these modern ideas which basically to their taste appended the standings of society. The good old days, we knew what is a good painting and what is a bad painting. Now come all kinds of surrealists and cubists and paint blotches of color and claims that this is a painting. Or write novels that no one can understand what they want and come up and say that's literature. And the same for them was also physics. Once upon a time, physicists were very connected to clear and intuitive ideas. Time was time, space was space, things that you show in experiment were true. That's the good old, and they gave it a name, Aryan physics. Physics of the right type, of the right race of people. And in the beginning of the 20th century, the Jews came and put in all kinds of strange ideas. For example, relativity. For example, quantum mechanics. So it's very interesting that Stark, and also Leonard, that a lot of their experiments were explained by quantum mechanics were dead against quantum mechanics. This is stupid ideas about what's an electron is here and there, not here and not there, dead and alive cats. That can come only from the degenerate minds of Jews. That's Jewish physics. And Jewish physics is wrong, and the Nazi Party has to take a stand that we will teach in Germany Aryan physics and not Jewish physics. And okay, in the 20s, basically most people thought of them as a bunch of idiots that are coming and mumbling strange stuff, but in 1933 they came to power. And, well, suddenly science in Germany completely changed. First of all Jewish professors were thrown out from the universities. Most of them emigrated at this point. And suddenly you have these two gentlemen deciding what should be the curriculum in the university. And here they went into a clash with Heisenberg. Heisenberg was then already a professor in Leipzig and, well, couldn't swallow that quantum mechanics is nonsense. Couldn't even swallow that relativity is nonsense. And Heisenberg was, although not a member of the Nazi party, he was definitely right-leaning with credentials of someone that is a good German nationalist, certainly not a left-leaning Jew. So how do you solve this problem where you have this also Nobel laureate, famous Nobel laureate? Okay, you move and improve your theory. The Nazi party had already a sound policy about racial purity. You have Jews by race, and if you have this percentage of Jewish blood in yourself, you're a Jew and should be fired or deported or whatever. Now they improved it. They invented a new category, and that was a vice Jew, a white Jew. What's a white Jew? That's someone who basically is, from the genetical point of view, from the racial point of view, Aryan, completely German, but his mind was corrupted by Jewish thought, and therefore, although racially he is German, from the point of view of the party, he should be denied and considered a Jew. And they started with a whole campaign to stop Heisenberg from teaching in the university and getting him fired. And basically in 1937, 1938, Heisenberg was at a point that he wasn't sure that he would be left at position. Well, at this point, Heisenberg took two steps. One of them had a huge impact on the further development of Germany in the war and the end of the war. The second was more an anecdote, but an interesting one. Turns out that Heisenberg's father was a professor in the University of Munich, something in classical languages or something like that. Another guy by the name of Himmler, the head of the SS, his father was also a professor in Munich. He passed away, but Heisenberg's mother and Himmler's mother were friends. So as any good son does, when he's in problems, he went to his mother, said, could you check with Himmler to calm down all this rhetoric and stuff? And she talked with Himmler's mother, who had a word with her son, and they got to a compromise, basically that Heisenberg will stay in his position in Leipzig, will be allowed to teach whatever he wants, meaning relativity and quantum mechanics, but shouldn't associate this subject with this Jew Einstein. So instead of saying Einstein's theory of relativity, call it theory of relativity, don't mention its origin. And other interesting steps that came out from this thing is that Heisenberg started to feel that his position is not secured and he should do something about his standing in Germany, get involved perhaps in research that is connected with military applications in order to become too important to be touched. And at the end of the story, Heisenberg finished up as the head of the German nuclear project. It's an interesting story as itself. Why this project progressed much less than the American program. Why? Basically, they didn't arrive to anything useful, while the Americans finished up with working nuclear device. After the war, Heisenberg claimed that he stopped the project because he wasn't interested in developing nuclear weapons. This seems more as showmanship after the war to be on the good side of the winners. It has much deeper reasons. That's a whole story by itself. It has a lot of books were written about it, even a theater show by the name of Copenhagen, which has to do with Heisenberg's visit to Bohr in 1941, while Bohr was still in occupied Denmark, which, as in any good quantum story, has totally two versions about what happened there. Heisenberg says that he went to Bohr and tried to convince him that the West and Germany should get to a truce on the development of nuclear weapons. Bohr didn't speak about it, but his actions speak more than what he said. He almost immediately after this meeting escaped to the West and most forcefully emphasizes that the US should develop nuclear weapons. So, and actually his writings that were kept sealed for 50 years seem to indicate that in this meeting Heisenberg told him that we are on the verge of developing nuclear weapons and therefore the West should give up. And perhaps the most telling Heisenberg, which was a postdoc of Bohr and very close personal friend, after this meeting Bohr refused to speak with him at all, so one can get the gist of this meeting, but we see that all this the politics around it had a huge influence on the behavior of Heisenberg during the war and the whole German development of nuclear energy and nuclear devices during the war. Okay, so that was a bit of general musings about the characters that we met here in solid state physics. It's important to know that physics has also existence beyond the lab and technical developments. As everything, any human endeavor, it has strong influence on things that happen around it. Okay, so I'll stop here and we'll move back to the good old phonons and our attempt to understand what they are. Questions about those?
Richard, could you make a quick repeat on the phonons from the previous lecture?
Yeah, well, basically I didn't say anything about phonons, but I'll start at from the point where basically in the previous lecture, what did we do? We calculated the energy of atoms that are in lattice points. Okay, so then we came up with a question. What happens to the energy when we're not at zero temperature? Okay, what happens? It's clear. They move out of the lattice points. How do we calculate the energy of this situation where it moves out of the lattice point? What is the behavior of this lattice once it's not at zero temperature? That's our aim. So, how did we start? Well, if you remember, for molecular and ions, we basically wrote down explicit interactions between pairs of atoms or molecules in the lattice. That worked good for ions and molecular interactions. We don't know to do it for covalent and so on. But nevertheless, we can write a general two-particle interaction, two-atom interaction, and see what it actually teaches us. Like in many cases in physics, to garner the bulk behavior, the macroscopic behavior of something, fortunately, it doesn't depend crucially on the microscopic details. And that's our aim at the moment. We'll write down basically a Hamiltonian of these atoms and see what it teaches us about different physical properties of this lattice. And I'm already saying, although I haven't shown it, I will show it, that it will lead us to the fact that we have acoustic waves, and we'll see that we can quantize these acoustic waves. Okay, so I'm writing down
Abstract.
so the energy, the potential energy of a lattice I'm summing over all lattice points, meaning all particles in the lattice. I have some potential that I may know or I might not know how to write it down. And is the actual position of the particle that at zero temperature is at lattice point R vector. And what happens to it? It's a small movement around the original position. If temperature was zero, this would be simply zero. Now, because it's not at the lattice point, it's at some vector u, y vector, because it could be in any direction at any small distance from this lattice point.
Why is U not dependent on time?
It's dependent on time, but I'm now taking the energy, taking a snapshot, asking where each atom is and asking what's the energy at this given time. I'm not yet doing dynamics. In a moment, I'll do dynamics, but at the moment, not yet. Okay, so if I rewrite the potential energy, I just explicitly wrote what is this guy is simply a lattice vector, because any subtraction of two lattice vectors is still a lattice vector. Okay, you want dynamics? What do I do for dynamics? I have to write kinetic energy plus potential energy. Time will come up if I want to write equations of motions out of this Hamiltonian. The Hamiltonian for each particle. Particle has some momentum, has a mass, and we have the potential energies that I have written here.
Aren't we supposed to sum up all the p's?
And here I should write down some overall lattice points, because I assume in each lattice point I have one particle atom. In this case.
Richard, we refer to a particle as an atom, or as a, I mean.
Okay, so the way that I've written it here, each particle is one particle that can be described by 6 degrees of freedom. 3 are the momentum, and 3 are the position. That's how I wrote it. You can come and tell me, okay, it's not an atom, it's a molecule that has some positions and can have rotation and heaven knows what. Yes, then add it to your Hamiltonian. Let's start, and for this course also finish with the simple case. We will see at the end that we are actually I can answer your questions about certain physical properties even without going into the details of. It's enough to know to count how many degrees of freedom this is. On the other hand, if I have more than one particle at each unit cell, life becomes interesting, and we'll do it explicitly. Actually, there is Einstein's one of Einstein's most important contributions to this subject. Okay. To remind you, let's write a function of which depends on three on x, y, or z, or as we can write it here simply as vector r, and it's moved by a small amount a vector. Okay. So this is equal to f of r. Okay, what does that mean? I want to write it explicitly because sometimes when students look on this, in general, they miss the final point. What's vector A? It's x plus y plus z. Usual definition of a vector in 3 dimensions. Okay. That is the definition of grad. Dot, meaning it takes this and I take this, I multiply it, so at the end it's ax. Here's the same. Take a minute at home and write down all the components of this guy. How do I do it? Exactly by the definitions. A is what's written here. Del is just do x, x hat plus so forth. Vector multiplication, perform vector multiplication, square it, get the result. Okay, so at the end of the day, although this is a complicated expression, what do I have here?
Taylor expansion, partial derivatives.
No, what do I have here? What is the entity that appears here at the end of the day?
That's the first order.
A scalar, a number. F is a scalar function. I put in a vector, but a vector is at the end of the day I get a number out of it. It's also here, if I don't get a number, I did something wrong. Questions? Good. So why do I need this story? Because I'm going to expand this guy according to the Taylor expansion. At the end of the day, it's potential. Potential is a number. So I feed it with vectors. So, U in the Taylor expansion. Okay, the zeroth order. Remember, this guy is the A, the small movement, the small dislocation in the position. Okay, so this is phi of R, and this is phi of R plus A. Okay, so the first expression is simply all to the zeroth order, all the particles are at the lattice points. If all of the particles are in the lattice points, R minus R prime is still R. And I can just sum over all of them. I don't need to sum over R and R prime, multiply by n and divide by 2. As I explained in the previous lecture. Okay, so that's easy. That's the zero temperature. So I simply wrote down the grad F times A. A is this part, grad of phi is a grad part. Someone can tell me to what this is equal?
The grad of phi might be the force acting.
Mm-hmm. So, after an extremely complicated calculation, I know it's equal to 0. No, it's not a complicated calculation. It simply comes from the fact that if we start from equilibrium, we can't have a force on the particle, because if we add the force of the on a particle, it wouldn't be the equilibrium. Okay, so the first order of the Taylor expansion is simply 0 around the equilibrium, and the fact that I take it around R tells me that I'm doing it around equilibrium. Am I seeing puzzled looks? Someone wants to ask something?
How did we get the second part of this?
I'm just writing what's written here.
Okay. And where is the circuit in green part?
That's A?
Yes.
That's O.
Oh.
So only the second order.
Only the second order plays a role. It's a very usual occurrence in physics. That's why harmonic potentials rule. Anything around the equilibrium to first order is a harmonic potential. Could be that the harmonic potential goes to zero, but you can't have the first derivative around the equilibrium. Okay, so I have to treat I just wrote the second term. And this is a term I'll have to do something. Okay, let me write it a bit more specifically. Let's erase it. No, I won't erase anything. Okay, so I'm looking only on the harmonical part of it. This is zero and this is trivial. This is the thing of equilibrium. What did I do? Simply ax, ay, az, which is these guys, x, y, any combination xx, xy, xz, all of them appear. This square will give me one derivative of mu and one derivative of nu, which means do squared do x squared do squared dou x dou y, all 9 combinations. Okay. Looks scary.
Why is u mu a vector? Isn't it supposed to be a scale?
Which is a
U mu. Why is it a vector?
well, sorry, that's a misnotation. You're right. It should be just. Or, well, I could leave the vector because it's the x component of the vector u, but I think it would be less confusing not to. Yes.
Don't we need to summon mu and
Mu and
yeah, but don't we need to sum the entire energies?
so all these
okay,
are
okay.
summations.
I thought it.
Lots of summations here. Have to sum over all combinations of x, y, z for both mu and u, and all points r and r prime.
Okay.
I want to write it a bit differently. Okay, I'm stopping writing what's mu and nu. Mu and nu are x, y, z for each one of them.
Well,
Okay, what do I see here? Basically, let's see what is d mu nu first. Okay, this we simply get. This guy is just to avoid double counting while r is equal to r prime. No big deal, just a small detail, not very important. What is important is this form. What do we see here? Someone knows in mathematics how do I call this form?
It's sort of inner product.
Dirac something.
A bilinear form. We have here u times u with basically something in the middle. Think of it as a vector times a matrix times a vector. And that's all I need at the point. What is phi? What is the exact structure of D according to the potential? Will vary according to what is the interaction, what is the lattice, and so forth. But the fact that it's bilinear is extremely important. Why? If I have a matrix multiplied by two vectors, where did you run into such a situation?
In quantum physics.
In quantum physics all the time, right? What do I know from this structure? If I know how to diagonalize D, I will have some 3 eigenvectors, because it's a 3 by 3 matrix, with multiplied by u squared each time. Okay, it won't be along the axis of mu x, y, z. It will be other eigenvectors, but it's still 3. Why is that important?
Eases all calculations, maybe?
You can choose the basis to work with for the problem. And
First of all, I could choose the basis in order to get a much easier calculation of the problem. And even before it, I know exactly what is the thermodynamics of this system. Why? What did you learn in thermodynamics? If I have a system composed of particles that behave like p squared over 2m plus a potential energy k times x squared, what is the average energy per degree of freedom?
It's a half kT.
Exactly. So here, without doing any additional calculation, the mere fact that I can write the potential in this way tells me to second order in the Taylor expansion that, and this, after all this complicated calculation, I know that U is equal to U equilibrium plus 3NKBT. That's the temperature dependence of the internal energy of this lattice. And that's the beauty of theoretical physics. I assumed very little here. What did I assume? Pairwise interaction between the lattice components and
second order approximation.
second order approximation. That's all.
Why didn't we divide this by 2?
Boom. Because there is half there. Half kBT for each, 6 degrees of freedom, and particles that have 6 degrees of freedom. And why did I have to go through all this behavior? Because they have to be quadratic, the dependence. I know that the dependence on the momentum is quadratic. That's what I started my Hamiltonian with. The whole exercise here was to show that it's also quadratic in the potential. So we needed a bit of exercise, but at the end, it's quadratic, just because it has a bilinear form. What is this exact feature? I don't know at the moment. And basically, to get this result, I don't care. If I want to know the energy per lattice point or per particle, I divide it by n.
U equilibrium needs to be divided by n.
No, so I'm writing it as, well, it doesn't come out nice. For me, the only thing that is important for me is that it doesn't depend on temperature. Of course it is. Heat capacity, what happens to the internal energy per particle when I change the temperature is simply now the riddle that Einstein stood before is that at low temperatures the heat capacity is much smaller than this. And this is ironclad. We didn't assume nearly anything from the point of view of classical physics. Pairwise around equilibrium. At low temperature, we're certainly around equilibrium. It seems to be ironclad, no way to play with it. So, this is something that we'll deal with in the next lecture. What else? Before it, we wrote the Hamiltonian, but we didn't write the equations of motion. Once we write equations of motion, we'll see that the solution are waves. These are the elastic waves. Now, in order not to be buried with details, as an example, we'll do a one-dimensional system just because it's simpler. We'll do first a one-dimensional system which has only one type of electron, of atoms, which is exactly the same calculation, but simpler, no indexes, less indexes. So, and the second we'll do if we have two different types of atoms in our lattice. You'll see that the results are different. Okay, so we'll stop here and do this calculation in the next page.
No, no.
Thank you.